I'm going to first of all just talk a little bit about who we are. I'm today representing HAG Architects. And we are a relatively newly started company in Copenhagen. We've only existed for 3 years. I'm Kasper, and I'm a Danish architect. I practiced for 10 years in London and New York. I moved back to Copenhagen. I'm not originally from Copenhagen, but I moved back to Copenhagen 3 years ago and started HAG Architects with 2 other partners. We have actually, one of my partners is Thomas Jensen, is a ex-Zaha Hadid senior architect, and he actually worked on the project that Birgitta was showing before. So the wooden Cambodia structure is actually his project. My other partner is David Gearing, who is actually a little bit more well known in this area, and it's actually the reason why we got invited, because he is, I'll talk a little bit more about that, but he has been a part of a big research project about, let's say, the promotion of wood in the building industry in the Scandinavian countries and in Denmark in specific. So what we do as HAG is we actively combine these 3 circles here: academia, research, and practice, with the purpose of building buildings, is really what the end goal for us is. So in academia, we are currently teaching at the Architectural Association in London, where we're looking at small-scale 3D printing, not with wood. And I'm not going to be talking too much about that. I think there's other bigger projects that are a little bit more relevant to look at. We previously taught at the Bartlett School of Architecture in central London, and as well as in Aarhus School of Architecture in Denmark. In terms of research, I have personally done some research at the Royal Academy in Copenhagen, where I've been looking at specifically at wood joinery at the Center of Information Technology and Architecture at that academy. We have just recently started a research project, which I'm also going to be showing at the Aarhus School of Architecture. And then, of course, there's Core Connection, which is David's sort of background. So David, our senior partner, was working for, before he joined us, was working for Core Connection, which is a green think tank in Copenhagen, and he was the project manager for this Go to Wood initiative, which was about promoting wood as a building material in the building industries in Scandinavia and specifically in Denmark. And it's all about implementing, let's say, the 17 Sustainable Development Goals that the United Nations have put out. I'm not going to go through too much of the, let's say, the environmental part of this. We'd have to ask David to come back and teach us more about that. I'm actually going to be focusing more on the digital implementation of, implementation of digital technologies in design, in architecture, and specifically with wood. And I have a couple of, let's say, main themes that we are looking at specifically in our office that we're interested in, which I'm going to be talking about. One is the relationship between computationally aided building techniques versus conventional building techniques. And the reason why I think this is interesting and very important to talk about also in this context about when we're talking about additive manufacturing is we have to realize that we're operating within an industry that is so heavy, so slow, and so moving ahead a lot slower than we who are thinking about what we could do in fact are. So that means that if we want to get stuff built, we have to meet, let's say, the industry halfway. So I'm going to be talking a little bit about that and also showcasing some of our projects. So that means that if we look at the construction process, this is some slides from my research at the Academy in Copenhagen. If we're looking at the construction process, and this is different from country to country, what we call the phases. In the UK, we call them phases A to whatever, K, U, something. In Denmark, we call it something else. In the US, we call it something else. In Sweden, we have something else. But if we just look at it from the building industry or the construction process, all the way from idea through to completion and maintenance, What we're starting to see now with the emergence of digital technologies, both in terms of design and manufacturing, is what we call a sort of a data flow. So we have information flowing between all phases of the project, all the way from ideation through to completion. So that does not only mean that we can actually track data information back to previous phases, we can also simulate what might happen in the phases to come. So that means that when we're talking about and looking at what the idea for the building might be, we can already simulate with digital technologies how the assembly sequence might be, or the maintenance even. And what I looked at specifically in my research, and which I think is interesting when you're comparing, let's say, additive manufacturing to subtractive manufacturing, is the assembly, right? So when we're looking at wood, traditionally, it's all about putting small parts together, right? Because we know a little bit, and I'm not going to be talking too much about this because we have material specialists, but we know that wood is a finite material and it's an anisotropic material, which in essence is a little bit contradictory to what you can actually do with additive manufacturing, right? It's a continuous material typically that we get out of when we're working with additive manufacturing, whereas with traditional wood building, we actually have finite elements. There's a limit to the extent in which we can have a column or a beam or a smaller component. Oh, I thought I had actually cut that one off. It was just to talk briefly about the complexity of the process that a building goes through, but also the amount of stakeholders. It's just because I want to, when we're talking about additive manufacturing, we have to be very aware of the fact that that is only a very small process of the entire building process. There are contractors, there's engineers, there's architects, there's users, there's all sorts of other things that we have to think about. So when we're looking at assembly traditionally, there's actually two things, and this is the way we work with it in our office. There's two scales that we have to operate on. One is what I called in my research the global scale, and one is the local scale. The global scale is about the logistics of putting a building together. So all the elements, they might be manufactured in a plant somewhere, then they have to be stacked, they have to be put into a lorry, they have to be shipped to the site, and then they have to be unloaded and blah, 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 blah. So there's a whole massive logistic, let's say, preparation that has to be taken care of. On the other hand, we have the local scale where we're looking at something very specifically, right? We're zooming into the tectonic scale. How do things actually click together? Is that something that's even relevant when we're talking about additive manufacturing? Might be a relevant question. And if we look at other industries outside of architecture, such as, for example, product designing of cars or shoes or whatever, a lot of research has already been developed into how to create efficient production lines. How do things actually come together, and in what order, and what materials? It may be various materials. And in that research, it's usually referred to as logistic assembly planning versus geometric assembly planning. But those two are tied together, right? So when you make a choice about how the geometry looks like, it has an impact on how big the lorry can be, for example, or vice versa. If you decide that you cannot use a lorry, then it has an impact. You can only transport an element in a smaller, by a smaller method that has an impact on the geometry, to put it roughly. So there's a mutual relationship when we're thinking about designing. The other interesting thing that I'd like to mention as well is these ideas of design for assembly and disassembly is something that in product design, we know from product design research, we know that we can actually simulate in a digital language. So the way, I'm not going to go into the depth of how we actually code and program how things are put together. I'm just going to be very sort of overall about it and say if we want to, let's say, plan how a structure comes together from a whole series of parts, when we simulate that in the computer, the way we do it is by looking at the final product and then taking it apart. So basically designed for disassembly. And the interesting thing about that is that it's very relevant when we're talking about environmental issues, because it's ideal to be able to take a building apart and maybe move it somewhere else, or dispose it, reuse it. Fast slides. It's just to get you into the world that I'm kind of in terms of the research. These are some examples of how a computer would read an assembly plan. This is called the directional blocking graph, and I can best illustrate it by the diagram that we have up here. P1 is blocking P2 from moving vertically. However, P2 can move horizontally, right? That's the way we can take them apart. And that's the way the computer can actually read how and simulate how a building is put together. So that means that even though we can actually produce something extraordinarily complex with wood and digital technologies, there's a whole other aspect about it, which is about how do we put the whole thing together in the end, right? So this is an example from Kenko Kuma's project, the Nine Bridges Golf Club in South Korea. So actually the whole process of assembling, and I would like to think of, or have us think about, whether that would not also be the case if we introduced additive manufacturing into working with wood. Because traditionally what would happen is, for any project, whatever project it is, there's a whole series of ways in which we can put things together. Like we can do it by hand, we can do it by jig, we can do it by robot, we can do it by heavy machinery. What about pre-assembly and what about on-site assembly? Do we do it full? Do we do it in modular? So there's a whole series of ways in which we can think about how to put a project together. And the reality is that it's usually a combination of several, right? So for example, for the golf club, they're using a jig to put a part of the building together, but also using heavy machinery to put the whole building together. And on top of that, there's probably parts that are going on with by hand or whatnot. Sorry, clicking the wrong one. Okay, so that's a little bit of a lineup of the thoughts that we are actually working with in our office when we talk about design for disassembly, but also looking at the relevance of how much is it actually relevant to use digital techniques, and to what extent can we just get further with conventional techniques? How do we combine the two? This is a project example from, it's a project we did with Lassa Architects, which the next speaker, Manya, was actually doing the calculations for. It's actually a concrete building, but the interesting thing about it, and the reason why I wanted to show it today, is because we did a huge wooden formwork in order to be able to produce this thing. And my sort of main message when I show you these projects that I'm gonna show you now is that the way we look at it when employing digital techniques, both in design and manufacturing, our point is it should not only be for efficiency, it should be to increase quality. So when we think about how to 3D print with wood, it should not only be for efficiency like we see with the 3D printing of the Chinese houses, it should be to increase the quality and the creativity, and what Birgitta was also talking about, not just letting the tools do the work, right? It's about the people that are actually using the spaces and so on. This project is, I'm going to show it in reverse. It's a crazy design. It's full of curves, and we've really tried to open up, let's say, the creative box, and we luckily had a client who was willing to do that. So like I said, it's a concrete building. It's a concrete shell that sits on top of just straight extrusion concrete walls. And just a little bit about what the project is. It's situated in Greece, so you have to imagine that it's sitting on a slope facing down towards the water, which is in the far distance. It's in a beautiful olive grove. I've taken out some images to cut down the length of my talk. And what we did is we luckily had a client who allowed us to just go bananas on all the design parts that we wanted to. So we got some really nice results. But basically the way that the building is designed is that so vertically up in that direction is actually south, and that means the building is sort of looking towards the view. But other than that, what we did is we considered it as a lump of earth, which we have scooped 3 exterior terraces out of, right? So there's one terrace there towards the south, one towards the east, which is the morning terrace, and one towards the west, which is the evening terrace. So you can kind of use the house. Of course, in Greece, you stay out all day, right? So that's what we used to be the design driver. So in the morning you'll use this one, in the afternoon you'll use this, that one, and then you go to in the evening to this one over here. And you can see these in these shadow diagrams how that works. Other than that, it's a very simple house. 1, 2, 3 bedrooms, a big open communal area, and entrance there. The special parts is, again, the terraces as well as the roof. And the roof is actually what I wanted to be talking about when it comes to wood, because this is where we decided to be creative with wood. What it is we managed to convince the client to buy us a CNC cutter that we could install in our basement in the office in Brussels. So initially we wanted to do the whole thing in foam and just have a contractor come and pour concrete all over it. There's a whole series of reasons which had to do with environmental issues, but also transportation. So again, logistic assembly planning, right? Which meant that we ended up having everything cut in our basement just below our office, because that meant that we could test everything in 1-to-1, go down, put it together, take it apart again. Does it work? Okay, great. In the lorry, then it goes off to Greece, right? And of course we had a central model, like you can see, for those of you who are familiar with it, is a big sort of parametric model where all components are linked to each other. So when we change the overall geometry, all components change with it. And in the end, when we had all sort of design parameters included into it, we more or less baked the geometry, and then we started printing the parts. So these are drawings of all the parts that went into it. And of course we used, as a byproduct of that, we used the CNC cutter to introduce all sorts of exciting spatial features. And we also used it to be able to control the geometry, as you can see here. This is, I mean, we were working together with standard builders. They were not specially trained contractors. There's a standard contractor. So we actually had to produce the formwork that allowed them to control the geometry precisely. And so this is a drawing that shows all the geometric sort of drivers that we worked with. And this is a photo from the building process. All the vertical walls were poured already. Not too difficult for the guys to control. And then what we did is we started just building a scaffold from the inside. The contractors would put the scaffold, and we would come with everything that we had cut in Brussels and put it on top. And the installation took 3 days. Because we had planned it very well in advance, it was just chuck, 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 chuck. Well, there was a little bit in the beginning. There was a freak out the first afternoon, maybe. But it went relatively fast. So I think this is the day after or something like that. The house is sort of something like 200 square meters. But it looks a bit bigger. But that's actually because one of the ideas of the house was that the roof would become an extension of the garden, so that you could walk directly from the garden up on top of the roof, where you have even more spectacular views. And also, you don't just steal a beautiful garden away from the existing. You just elevate it above the roof. On top of that, there's a whole series of environmental things that also are great because of heat and things like that. Having a green roof is actually quite good in Greece. But so you can see, it was it was a fun project to do because the installation of all of these wooden panels, this entire wooden formwork, was something that we, the architects ourselves, this is not a traditional way of doing it. We went there to Greece, bought a ticket, went to Greece, went and assembled the whole thing together with the contractors. And of course that allowed us to control the geometry to a very large extent. So just images from the installation. The roof above the main living area, sorry, the ceiling above the main living area, we did something interesting. Again, a creative sort of move with the use of a wood, and this is the part that Manya actually did the calculation for. Instead of just accepting that the entire formwork would be used to pour concrete on and then taken down and thrown in the ocean or burned or whatever, we actually, in this part, decided to leave the formwork in there. So we would cast the concrete would set, and a part of the roof would be able to taken down. Oh, here you can see some, here it is. This is after the pouring of the concrete, as you can see it here. This out here was actually a part of the formwork. So we would only take half of it down and the rest would remain. So it's sort of what we call a lost formwork. And that's the end result. Another example of the exact same sort of concept is a project that we did recently. It was finished last year as a restaurant in Melbourne. I'm going to go through this relatively fast. How are we doing with time? It's okay. It's the same case. The only reason why we even managed to convince the client to give us some creative freedom was because we could produce, test, assemble everything in Denmark, take it apart again, put it in a container, put it on a Maersk ship across the Indian Ocean, and it would arrive in Melbourne 3 weeks later or whatever, go there and then assemble. And the interesting part, of course, is that, you know, we're taking over a space which was a complete mess. And the drawings that we got from across the, you know, the other side of the globe, how is there any way of knowing whether, when it says on that drawing that that wall is actually 5.251 something meters, there's no way of testing, right? So we actually included that idea of assembly into the design, so that not only were we able to put it together in Denmark and take it apart again and ship it, but we also made sure that everything had tolerances that would actually accommodate the actual site. So here's just some drawings of that, of how everything comes together. And that's just before it goes to Melbourne, and then during the assembly process, very, very fast. One of the things that's, I mean, we have done a few restaurants. One of the things that's important when you're doing restaurants is that your client usually, you know, takes out a lease and then he wants to open the next day. It's like, I'm starting paying rent on the 30th and I want to open on the 1st because otherwise I'm losing money. So from that aspect, it's not a bad idea to have something which can be put up super, super, super fast. Okay, so there was a couple of build projects. Then this one is actually a research project, but which is going to turn into hopefully a build project. And for this one, I'm showing you this one because I think it's really interesting in terms of the relationship between conventional and digital use of conventional and digital production techniques. What it is it's a collaboration together with Faaborg Midtfyn municipality in the center of Denmark, and then the architecture school, Aarhus School of Architecture. And we got funding from the Foreign Ministry of Denmark to develop a project that would combine parametric production tools with cultural heritage. And which sounds a bit like, okay, so we have cultural heritage, which is about old buildings, and then we have parametric technologies, which is about looking into the future and innovation. But actually, those two, they really find a common ground in the, let's say, in the unique. When we're using parametric tools, it's very easy to let's say, establish rules that accommodate unique situations. And unique situations is definitely old buildings. So I guess in most countries in Europe, you have a situation where the urbanization of the big area, 2 minutes? Oh, wow, okay, shit. The urban areas, they just grow and grow and grow. So in the rural areas, we have empty buildings, some of them super, super nice. What do we do with them? Do we just tear them down, or can we refit them? So that was the task. In this case, this is an old Fabersfabriker. So it's a factory that used to produce curtains, actually. Which was, I think they moved the production to the Far East 15 years ago or whatever. But it's a very beautiful building actually from many aspects, although it's an old industrial building. Do we tear it down? Right now it's just there, it's dilapidating completely. Or can we refit it? So the project that the municipality gave us is to actually propose transforming this into apartments. So, okay, I have to speed it up a little bit. What we did is we used a new technology called, well, it's not a new technology, it's been used before, but we produced a cloud, a point cloud basically, which is a 3D scanning of the entire building. That gives you an exact geometry of what is actually there. Then we did a whole big long research where we're exactly comparing the conventional faces versus what they would look like when you're using parametric tools. And this actually refers back to one of the first slides I had where I was talking about this data flow that goes back and forth. Then we looked at different types of transformation strategies. You know, exterior cladding, interior cladding, infill, combinations, additions. There's all sorts of things that you can do. And we decided in order to make an example for this factory, to pick out two transformation strategies. One is we called it the pod, so it's a container, right? So it's like building a container and then just pushing it into the existing space. Whoops. And then what's it called? The partition wall. Which part is actually relevant to produce using digital techniques, and which for conventional techniques? You take a section through the point cloud, you get something weird because it's an old building. In this case, there's arches. You get an exact outline of where to put the partition wall, which is this. And then we actually analyzed which part is relevant to use conventional techniques and which part is relevant to use digital techniques. And actually, it's the whole periphery that actually connects or becomes the interface to the existing building. The rest of it in here can just be industrial standards. So that's how we literally split it in two. And then we produced a series of components that actually, again, designed for assembly and disassembly, has a very specific assembly sequence to it. First, the whole periphery, and then industrial standards, click, that's it. And then there's something, I'm not going to talk too much about that because I don't have time. There's something about the integration of technical aspects. We did exactly the same technique for the pod, right? So all the peripheral areas are digitally fabricated, and the central ones are industrial standards. So what we get is actually a system that is sort of a multinodal system. We can go in all directions, and everything can either be pre-assembled in a factory, or it can actually come in components and be fabricated or put together inside the factory. So this is just examples of visualizations of how that would actually go together. So that's more or less the modular system as it is right now. And then there's something we have, how you can vary the length so that it can actually adapt to the dilapidating building. And this is just some examples of what that might look like. So remember, this is an interior project, so it's not structurally proven yet. And here you have it inside the point cloud. Okay, I'm just going a bit fast now. Oh, I thought I had taken some of these visualizations out. And here's where it's at the moment. This is a one-to-one mock-up, which is produced in the Aarhus School of Architecture. Okay, I have 2 slides to show on this one, and then I'll round it off. We're together with Manya, actually. We're working on and I think it's relevant also in this context. We've been commissioned to produce a concept for micro-housing for multi-generational communities in the United States. So there's a big shortage of housing. And actually what it is, never mind the sort of layout or the house design, but the system that we're working on is all CNC manufactured. There's not a single thing except for some bolts and some brackets that's not CNC cut. It's the whole thing. And the reason why I'm showing this, I mean, this is very early stages, and this is a mock-up they did earlier. The reason why I'm showing this is because actually a lot of the sort of the questions that we often get is like, why not just do a standard post and beam structure out of wood? It's super simple. That you just go down into Homebase and get your products and put it together. You can do that very cheap and easily. So this is free for me to say because it's not been proven yet. But the client who are actually producing these mock-ups are claiming that the only reason why this can become a market product and even be competitive is because of the technologies. So that's the reason why, that's what I ended up with, saying. They claim that the technologies are gonna enable them to be competitive. It's just when thinking about the implementation of additive manufacturing techniques. Last slide. The conclusion is, at the moment in the research project we did, 15% is all that's necessary in order to make it the most efficient project, whereas the rest of it, 85%, you might as well use standard conventional labor. Could this change in 20-something? Could it be 70 versus 30? Where are we headed? That's the sort of open question that I'm leaving you with. Thank you.